this is something, it should be kind of similar to you. Just the equation that we use is a little different. So we have an equation in the form y equals kx. And if you notice, it's kind of like slope-intercept form. Y equals something times x plus b, right? mx plus b. So all it is, it's the exact same thing, except there's no y-intercept. So that means all of our direct variation graphs, everything in direct variation form in this y equals kx form, is going to go through the origin. Because the y-intercept is 0, there is no y-intercept. So it's always going to go through the origin. And we call this k, we call that the constant of variation. Well, let's think about this. It's constant of variation. So it varies at a constant rate. So what else do we just learn that has a constant rate of change? What's the same thing as a rate of change? A little slope, isn't it? So this k is actually the slope of your line, because that's like your rate of change, your constant rate of change, how it varies at a constant rate. So that's why it's called the constant of variation. It's really just the slope. So the number prior to x is just the slope. So in this case, I graphed y equals x, which is really y equals 1 times x. So I have a slope of 1, which is really 1 over 1, rise over run, which I graphed right here. So everyone's going to go through the origin, and it's going to be in the form y equals kx. So y equals the slope times x, or the constant of variation times x. First thing, pretty straightforward, name the constant of variation. Then find the slope of the line that passes through each pair of points. Well, didn't we just say that these two guys are the same thing? So that's pretty easy, right? So I can abbreviate this. Constant of variation, I know is 2. It's just the number that's in front of your x. As long as I have it in that form, y equals kx. As long as it's in this form, I can just look at the coefficient on x. And the slope, I could put m for slope, or actually write out slope, is the same thing, isn't it? Exact same thing. Pretty straightforward, pretty easy. Same thing over here. It's in y equals kx form, so I could say the constant of variation is -4, or you could say k if you want to. It doesn't matter. M for slope is also -4. As long as it's in the y equals kx form, pretty easy. To graph it, well, one way we can always graph this way, is by making a table. Right? XY table, we just pick some x values. It doesn't matter what you pick. Here, since I have a 2 in the denominator, I might pick even numbers to graph. But you don't have to do that. Because why? We already know a point on the graph, don't we? It goes through the origin every single time, doesn't it? It always goes through the origin. And can't I tell what the slope of this guy is? -3 over 2. So here's my slope. Well, if I know a point on my graph, can't I just use the slope to find another point? Well, here's the tricky part. This isn't -3 over -2. Right? I'm not going to go down and left, because this would make a +3 over 2. So we're not going to use this. We got to give the negative to either the 3 or the 2. So I could either do -3 over 2, or I could do 3 over -2. So I'm going to do the -3 over 2, so that means down 3, right, because rise. So 1, 2, 3, and right 2, 1, 2. So there's a point. I could also go up 3 and left 2, because rise over run. 1, 2, 3, 1, 2. So there we go. There would be my graph of the line. And I don't even need to make the table then. That's a lot quicker than having to go through the math of making the table, because you know it goes to the origin. So anytime you graph anything in direct variation form, you know it goes to the origin, and then use your slope. Here's where we get a little more in depth. It says, suppose y varies directly as x. Here's my key. Y varies directly as x. That means I can use y equals kx. I can use direct variation. Y varies directly as x. Write a direct variation equation that relates x and y, and then solve. So all I'm going to deal with, it says if y equals 9 when x equals -3, find x when y equals 15. So I got a lot of information here. Deal with it piece by piece. So I'm only going to deal with this part first. If y equals 9, so I'm going to plug in 9 for y into my equation, y equals kx, when x equals 3, or -3. So I don't know what k is, and I know that x is -3. So here's my first part. I want to write a direct variation equation. So all I do is I just solve for k and plug it back in. Well, what am I doing with the k? I'm multiplying by -3, so the inverse is divide by -3. Whatever I do to one side, I do to the other. So k equals -3. So to write my equation, I just plug that in to my original y equals kx equation. So y equals -3 times x. So there's my equation. This is the first part that it's asking me. Write an equation. Then it states, then solve. So when we solve, now I can use any situation. I can say x is something and I can solve for y. I can say y is something and I can solve for x. So I can find any situation now. So what we do is it says find x when y is 15. So now I'm going to plug that 15 in for y into my equation down here. So 15 for y equals -3 times x, and we solve for x. So divide by -3 on both sides, and x would equal -5. So I need two answers there. I got to write the equation, y equals -3x, and then solve that second situation. Okay, the reason why we have direct variation is because we can use it for real world examples. It helps us find a constant rate that'll help us predict something in the future. So for example here, the Ramirez family is driving cross country on vacation. They drive 330 miles in 5.5 hours. Write a direct variation equation to find the distance t driven in time. Well, I got distance, rates, and times, don't I? So there's my dirt formula. So out of the distance formula, what part do you think is going to be the constant of variation? What's really the k? If I think y equals kx, that's my direct variation. Won't that be my rate? Right? My rate is really my slope, isn't it? The rate of how something changes. So the rate and the k are going to be the same thing. So when I set this up, write a direct variation equation, instead of using y equals kx, I'm going to say d equals rt. And what were we given? Distance is 330 miles. We don't know the rate, so we leave it as r. And the time was 5.5 hours. Well, I can solve for the rate now, can't I? I can find the miles per hour here. So we divide by 5.5, divide by 5.5, and we end up with 60. So my equation would be, I could find any distance that I drive, knowing that I'm driving 60 miles per hour for a certain amount of time. So now if I said, well, how much time is it going to take to travel 600 miles? I could plug in, 600 for D and then solve for T. It would show me how much time it's going to take. So this is why we find this equation. And then I might ask you to graph it. If I do that, same thing like we did before. This 60, I think about this. The 60 is really your slope, isn't it? And the d would be your y, because y equals kx, right? And your t would be your x. So all I would do is I would use that 60. And we know that it's going to go through the origin, correct? And then when you graph it, you just have to determine what you want to make your scale. Well, if I think my slope is 60, that's really 60 over 1. So a rise of 60, a run of 1. So I probably want to count by 1s on my x, because those are my runs. And maybe count by like 20s here. So then I know it goes to the origin. We already talked about that. All direct variations go to the origin because the y-intercept is 0. So up 60, you write 1. Up 60, you write 1. And that's everything on direct variation.